Imagine standing beneath a clear night sky, countless stars scattered across the darkness like diamonds on velvet. Your eyes trace constellations while an ancient question forms in your mind. Are we alone? The universe stretches before you, impossibly vast and impossibly old. Trillions of stars orbit within billions of galaxies, each potentially harboring worlds not unlike our own. For centuries, we've pointed our instruments upward and listened. We've sent messages into the void. We've scanned the heavens for any sign of intelligent life beyond Earth. And yet, silence. The stars remain quiet. No spacecraft from distant worlds hover above our cities. No ambassadors from other civilizations walk among us. The cosmos appears empty of voices that might answer our own. This silence feels almost impossible. In a universe so enormous, with billions of years of cosmic history, shouldn't someone have found us by now? Tonight, we explore what may be the most profound realization in our search for extraterrestrial intelligence. Why advanced aliens will never visit Earth. Not because they don't exist, but because of something far more fundamental. The answer lies at the intersection of physics, biology, and time. It involves distances so vast that they challenge our understanding of what's possible, even for civilizations that might be millions of years ahead of our own. We'll journey through the mathematics of interstellar travel, the limitations imposed by light itself, and the evolutionary pressures that shape all life in the universe. What you'll discover isn't a story of human insignificance, but rather a profound insight about the nature of intelligence across the young cosmos, and why the silence of the stars might actually be exactly what we should expect. Our quest begins with a paradox first noted by physicist Enrico Fermi in 1950. If the universe should be teeming with intelligent life, then where is everybody? Why haven't we been contacted? The answer may overturn everything we thought we knew about our cosmic neighbors. It suggests that the very technologies and evolutionary paths that create advanced civilizations also ensure they will never cross the vast distances between stars. Consider this. Our galaxy alone contains between 100 to 400 billion stars. If even a tiny fraction host intelligent life, millions of civilizations could exist simultaneously. Some might be millions of years beyond our development. Yet here we float on a pale blue dot, apparently unvisited and uncontacted. The night sky watches us in silence, despite our broadcasts announcing our presence for over a century now. What if this silence isn't evidence of our cosmic loneliness, but instead reveals a fundamental truth about advanced intelligence that we're only beginning to understand? As we look deeper into the night, we must confront the possibility that the greatest barrier between civilizations isn't technological, but is woven into the very fabric of space and time itself. Tonight, we'll examine the clues hidden in our own evolutionary history, the laws of physics that govern all things, and the mathematical certainties that may forever keep intelligent species isolated from one another. The journey takes us from the earliest human wonderings about other worlds to the cutting-edge theories that explain why, despite potentially millions of advanced civilizations, none have reached our doorstep. This isn't a tale of disappointment, but of cosmic perspective, one that might forever change how you view those silent stars overhead. We begin with a simple truth. Space is big, incomprehensibly big. The nearest star system to Earth, Alpha Centauri, lies 4.37 light-years away, a distance so vast that our fastest spacecraft would take tens of thousands of years to reach it. Even light, the fastest thing in the universe, requires years to cross these interstellar gaps. Our galaxy stretches 100,000 light-years across, meaning light itself needs a millennium to travel just 1% of this distance. And beyond our Milky Way lie billions of other galaxies, separated by millions or billions of light-years. The universe operates on scales that defy human intuition, scales that may present insurmountable barriers even to civilizations far more advanced than our own. What if the silence from the stars isn't because nobody's out there, but because nobody can get here? What if physics itself conspires to keep civilizations forever separated by the dark gulfs between stars? The evidence suggests that the more technologically advanced a species becomes, the more it realizes the futility of interstellar travel on any meaningful scale. Consider the energy requirements. To accelerate a modest spacecraft to even 10% the speed of light would require harnessing energy equivalent to thousands of nuclear bombs. And even at that impossible speed, the journey would take decades. Time itself becomes the enemy of interstellar explorers. By the time a message crosses the gulf between stars, the civilization that sent it might no longer exist. By the time a ship reaches its destination, its home world could be unrecognizable. These aren't merely human limitations. They're constraints imposed by the fundamental laws of nature. Laws that apply equally to all beings throughout the universe, regardless of how advanced their technology might be. As we explore these cosmic barriers tonight, we'll discover that they don't diminish our place in the universe. They help explain it. They tell us something profound about the nature of intelligence and its relationship to the vastness of space. The great silence from the stars may be the universe's way of revealing one of its deepest truths. That intelligence, wherever it emerges, becomes bound to its home world or star system by the unforgiving mathematics of cosmic distances. This is the story of why, despite potentially millions of advanced civilizations scattered throughout the cosmos, Earth remains unvisited. And why, perhaps, that's exactly what we should expect. The journey begins now, as we unravel the cosmic paradox that has puzzled humanity since we first looked up at the stars and wondered, where is everybody? Chapter 2: Cosmic Loneliness and Human Meaning. The question of extraterrestrial life touches something primordial within us. Since our ancestors first gazed skyward, we've wondered if other beings share the cosmos, if we are unique or merely one note in a universal symphony. This isn't merely scientific curiosity, it's existential. The presence or absence of other intelligent life shapes how we understand our place in the universe and the meaning of our brief existence. When we search the stars for companions, we're really asking fundamental questions about ourselves. Are we special? Are we alone? Does our existence matter in the grand cosmic scheme? Throughout human history, we've alternated between believing ourselves to be the center of creation and fearing our cosmic insignificance. The truth likely lies somewhere in between these extremes. The absence of visiting aliens doesn't mean we're alone in the universe. Rather, it suggests something profound about the nature of intelligence and its relationship to the vast distances of space. If advanced aliens haven't visited us, it may reveal not that we are unworthy of attention, but that the universe itself constrains even the most advanced civilizations through fundamental physical laws. This perspective offers a kind of cosmic comfort. We aren't being ignored or overlooked. We aren't insignificant. Instead, we may be participating in a universal pattern, intelligent life emerging, but remaining largely bound to its home systems. Consider what this means for human purpose. If advanced civilizations throughout the cosmos eventually discover the same truth, that the stars remain forever distant, then perhaps the purpose of intelligence isn't to conquer the galaxy. Perhaps instead, intelligence evolves to understand and appreciate its home world. To discover the universe not through physical travel, but through observation, mathematics, and the development of science. This realization doesn't diminish our cosmic significance. It reframes it. We may never meet other intelligent beings face to face, but we share with them the profound journey of understanding the universe from our respective cosmic shores. The night sky, then, becomes not a reminder of our isolation, but evidence of our connection to something greater, the emergence of consciousness capable of comprehending the cosmos. When we look up at the silent stars, we're engaging in an activity potentially shared by countless other beings on distant worlds, wondering, questioning, seeking to understand the magnificent universe that gave us birth. The absence of visitors could suggest that intelligence throughout the universe eventually turns inward rather than outward, finding meaning not in the conquest of space, but in the deepening of understanding. Perhaps advanced civilizations discovered that the most profound frontiers aren't between stars, but within consciousness itself, within the mysteries of existence that can be explored without ever leaving one's home world. This perspective offers an antidote to cosmic loneliness. We aren't abandoned in a cold, empty universe, but part of a natural order where intelligence emerges, questions, and eventually discovers its purpose within its own sphere. The silence of the stars doesn't speak of our isolation but of a shared condition, the universal experience of intelligent beings coming to terms with the vastness of space and the limitations it imposes. In this light, our search for extraterrestrial intelligence takes on new meaning. We may never receive visitors from distant stars, but we might someday detect signals that confirm we aren't alone in our questioning. Even this limited form of contact would transform human understanding. To know with certainty that others exist, even if we never meet them, would forever change how we see ourselves and our place in the cosmos. Our cosmic significance lies not in being visited, but in being seekers, in our capacity to wonder about the stars and to understand, eventually, why they may forever remain beyond our physical reach. The universe has granted us something precious, consciousness capable of contemplating its own origins. This gift is no less valuable if it turns out to be shared by countless others who, like us, remain bound to their home systems. Tonight's journey explores not just why aliens won't visit Earth, but what this tells us about the nature of intelligence throughout the universe, and what it means for our own search for purpose. This perspective offers a profound kind of hope. We aren't cosmically insignificant beings awaiting validation from superior aliens. We're participants in the universe's grandest story, the emergence of consciousness capable of understanding itself. If our exploration tonight reveals that advanced civilizations throughout the galaxy eventually discover the impossibility of interstellar colonization, this doesn't trap us in a smaller universe. It connects us to a universal experience. The stars may remain forever distant, but in that very distance lies a shared challenge that potentially unites all thinking beings. We may never meet our cosmic neighbors, but we walk parallel paths. Our human story becomes not one of cosmic isolation, but of participation in something universal. The journey of consciousness, awakening to itself and to the magnificent cosmos that created it. As we explore the scientific reasons why advanced aliens will never visit Earth, remember that these same forces shape all intelligent life. The laws of physics, biology, and time that constrain us constrain them as well. This common framework suggests a kind of cosmic community, not of travelers meeting face to face, but of thinkers separated by light years yet united by the same questions and the same fundamental truths. Perhaps the greatest purpose of intelligence isn't to conquer space, but to understand it, to develop science, art, philosophy, and wisdom that reflects the universe back to itself through conscious minds. If this is so, then Earth isn't an overlooked backwater awaiting discovery. It's one of countless crucibles where the universe has evolved the capacity to know itself, a purpose no less profound for being shared. As we journey deeper into the reasons behind the great silence from the stars, we'll discover that what initially seems like a limitation might actually be the foundation for a deeper understanding of our cosmic significance. The absence of alien visitors invites us to reconsider what truly matters in the story of intelligent life, not conquest or colonization, but understanding, wisdom, and the discovery of meaning in our brief moment of existence. This is the gift hidden within the paradox we explore tonight. The revelation that our cosmic purpose might not be to reach the stars physically, but to comprehend them, and in doing so, to understand ourselves. Chapter 3. From Ancient Wonder to Modern Science. The human fascination with potential life beyond Earth stretches back to our earliest civilizations. Ancient Greek philosophers like Democritus and Epicurus proposed the existence of infinite worlds, potentially harboring other beings. The atomists of ancient Greece suggested that in an infinite universe, matter would eventually arrange itself into every possible configuration, making other inhabited worlds not just possible, but inevitable. As early as 300 BCE, Epicurus wrote, "There are infinite worlds both like and unlike this world of ours. We must believe that in all worlds there are living creatures and plants and other things we see in this world." This wasn't just philosophical speculation. It represented humanity's first attempt to extrapolate from our limited experience to a cosmic perspective based on natural principles rather than supernatural explanations. The Greek concept of the plurality of worlds persisted through history, though often in conflict with religious cosmologies that placed Earth and humanity at the center of creation. In medieval Islamic astronomy, scholars like al-Biruni and Ibn Sina contemplated other inhabited worlds, developing ideas that would eventually influence European thought during the Renaissance. By the 16th century, Copernicus had displaced Earth from the center of the universe, setting the stage for a revolution in how we understood our cosmic position. Giordano Bruno expanded on Copernican ideas, proposing in 1584 that the stars were distant suns potentially orbited by their own planets where other beings might dwell. For these heretical ideas, Bruno was burned at the stake. The invention of the telescope in the early 17th century transformed these philosophical musings into scientific inquiry. When Galileo first pointed his telescope at the moon, he saw mountains and valleys, suggesting worlds not unlike our own. As astronomical instruments improved, so did our understanding of the planets. Mars, with its polar caps and changing seasons, seemed particularly promising as a potential abode for life. By the late 19th century, American astronomer Percival Lowell believed he saw canals on the Martian surface, evidence, he thought, of an advanced civilization engineering their environment to survive on a dying world. These canals were later proven to be optical illusions, but they captured public imagination and sparked a wave of science fiction centered around Martian civilizations, most famously in H.G. Wells' The War of the Worlds. While Mars captured the public imagination, scientists began considering a more fundamental question. How would truly advanced civilizations make their presence known across interstellar distances? In 1899, Nikola Tesla claimed to detect signals from Mars while experimenting with radio receivers in Colorado Springs. Though his claims were never verified, they represented the dawn of a new approach to finding alien intelligence. The concept of using radio waves to detect extraterrestrial civilizations gained scientific legitimacy in 1959, when physicists Giuseppe Cocconi and Philip Morrison published a paper suggesting intelligent beings might communicate via microwave radio signals. Their paper, Searching for Interstellar Communications, proposed that the radio frequency of 1,420 MHz, the emission frequency of hydrogen, the most abundant element in the universe, would be a logical channel for interstellar contact. This sparked the birth of modern CT, the search for extraterrestrial intelligence. In 1960, astronomer Frank Drake conducted the first modern SETI experiment, Project Ozma, listening for artificial signals from nearby stars. Drake later formulated his famous equation, a probabilistic argument used to estimate the number of active, communicative extraterrestrial civilizations in our Milky Way galaxy. The Drake equation considers factors like star formation rates, the fraction of stars with planets, the number of habitable planets per star system, and the longevity of technological civilizations. Depending on the values assigned to these variables, the Drake equation can yield estimates ranging from thousands of communicating civilizations in our galaxy to less than one, effectively suggesting we might be alone. But if there are thousands of advanced civilizations in our galaxy, as some interpretations of the Drake equation suggest. Then we face a profound paradox first articulated by physicist Enrico Fermi in 1950. During a lunch with colleagues at Los Alamos National Laboratory, Fermi reportedly asked, "Where is everybody? If the universe should be teeming with intelligence, why haven't we detected it?" This Fermi paradox has become one of the most compelling puzzles in our search for extraterrestrial intelligence. It forces us to confront the contradiction between high probability estimates and the lack of evidence. One early response was the zoo hypothesis, proposed by John Ball in 1973, suggesting that alien civilizations might be deliberately avoiding contact with Earth, preserving us like an exhibit in a cosmic zoo. Another explanation, the Great Filter hypothesis, suggests that some extremely difficult evolutionary step prevents most life from reaching advanced technological status, and we don't know if humanity has passed this filter or if it lies ahead. More optimistic perspectives suggested we simply haven't been looking long enough or in the right ways. The universe is vast, and our SETI efforts have examined only a tiny fraction of potential signal frequencies and directions. As our understanding of planetary science evolved, so did our appreciation of the potential rarity of conditions suitable for complex life. Perhaps technological civilizations are simply much rarer than early optimistic estimates suggested. The discovery of exoplanets, planets orbiting other stars, beginning in the 1990s, transformed these discussions from theoretical to empirical. We could finally begin to assess how common potentially habitable worlds might be. NASA's Kepler mission, launched in 2009, revealed thousands of exoplanets and suggested that perhaps 20 to 50% of Sun-like stars might host potentially habitable, Earth-sized worlds in their orbital Goldilocks zones, with billions of stars in our galaxy alone. Even conservative estimates suggested millions of potentially habitable worlds. The question of where is everybody became even more puzzling. Scientists began focusing on the engineering challenges of interstellar travel, calculating the enormous energy requirements and timescales involved. The physics of space travel emerged as a possible explanation for the silence. Another approach examined the evolution of technological species. What if advanced civilizations typically destroy themselves through nuclear war, climate change, or other self-inflicted catastrophes before achieving interstellar capability? Another approach examined the evolution of technological species. What if advanced civilizations typically destroy themselves through nuclear war, climate change, or other self-inflicted catastrophes before achieving interstellar capability? Alternatively, what if technological evolution follows predictable paths that lead not outward to the stars, but inward toward virtual realities, or forms of existence fundamentally different from biological life as we know it? These questions merged astronomy with anthropology, psychology, and evolutionary biology. Understanding why we haven't detected aliens required understanding not just the cosmos, but consciousness itself. By the early 21st century, our search had grown more sophisticated. Radio telescopes scanned the skies while optical SETI looked for laser signals. Infrared searches sought the waste heat of massive alien engineering projects. As we developed better tools to study exoplanet atmospheres, we began planning how to detect biosignatures, chemical evidence of life, and technosignatures, signs of technology on worlds orbiting other stars. Yet despite our increasingly powerful instruments and expanding search strategies, the silence persisted. And in this silence, a more profound explanation began to emerge, one based not on the rarity of life, but on the nature of physics itself. Chapter 4. Facing Cosmic Scale and Distance. The universe operates on scales that defy human intuition. To understand why advanced aliens won't visit Earth, we must first grasp the true magnitude of cosmic distances and the physical laws that govern all beings, including those far more advanced than ourselves. Let's start with our cosmic address. Earth orbits an average star at a distance of 93 million miles. Light from the Sun takes about 8 minutes to reach us, a distance we call 1 astronomical unit. Our solar system extends far beyond Earth. Neptune, the outermost major planet, orbits at 30 astronomical units. The Voyager spacecraft, launched in the 1970s and now entering interstellar space, have taken over 40 years to reach this distance. The solar system itself is surrounded by the Oort cloud, a sphere of icy objects extending perhaps a light year from the Sun. At this scale, we've barely left our cosmic neighborhood. Beyond our solar system lies truly empty space. The nearest star system, Alpha Centauri, is 4.37 light-years away, over 25 trillion miles. Light itself, traveling at 186,000 miles per second, requires more than 4 years to cross this gap. To understand this distance, consider that our fastest spacecraft, traveling at about 38,000 miles per hour, would take over 70,000 years to reach Alpha Centauri. And this is merely our nearest stellar neighbor. Our Milky Way galaxy contains between 100 to 400 billion stars scattered across a disk 100,000 light-years in diameter. If you shrunk the galaxy to the size of North America, our solar system would be smaller than a grain of sand. Even if we could somehow travel at the speed of light, which physics tells us is impossible for any object with mass, crossing our galaxy would still require 100,000 years. At more realistic speeds, millions of years. And beyond our galaxy lie billions more, separated by millions or billions of light years. The observable universe stretches 93 billion light years across, containing perhaps 2 trillion galaxies, each with billions of stars. These vast distances aren't just challenges for human technology. They represent fundamental barriers imposed by physics itself. Even for civilizations millions of years more advanced than our own. The speed of light isn't merely a current technological limitation. It's a cosmic speed limit woven into the fabric of space-time itself. Einstein's theory of relativity, confirmed by countless experiments, establishes this limit as absolute. No physical object with mass can reach or exceed the speed of light. As an object with mass accelerates toward light speed, its energy requirements approach infinity, a fundamental barrier no technology can overcome. Even if we imagine advanced aliens with nearly unlimited energy resources, the light speed barrier remains. And at sublight speeds, interstellar journeys become multi-generational projects spanning centuries or millennia. Consider the practical challenges. A civilization wishing to visit Earth from even 100 light-years away, a tiny distance in galactic terms, would face a journey of centuries each way, even at a substantial fraction of light speed. The energy requirements for such a journey are staggering. Accelerating even a modest spacecraft to 10% of light speed would require harnessing energy equivalent to thousands of nuclear bombs. And this for what purpose? To visit one of billions of potentially habitable worlds with no guarantee of finding anything of unique interest. The cost-benefit calculation simply doesn't compute, even for vastly advanced beings. Time itself becomes the enemy of interstellar explorers. By the time a message crosses the gulf between stars, the civilization that sent it might no longer exist. By the time a ship reaches its destination, its homeworld could be unrecognizable. Even if advanced aliens could somehow overcome these barriers through technologies we cannot imagine, why would they choose Earth specifically? Our planet has been broadcasting radio signals for barely a century. Those signals have reached less than 100 light-years into space, a mere bubble in our 100,000 light-year galaxy. From a cosmic perspective, we've only just announced our technological presence. And what would aliens find if they did visit? A pre-interstellar civilization still struggling with basic planetary challenges. Climate change, resource depletion, political division. What would motivate an advanced species to make contact? Some have suggested they might come for Earth's resources, but this fundamentally misunderstands cosmic economics. Any civilization capable of interstellar travel would have far easier ways to obtain any material resources they need. Water, metals, organics, all are abundant throughout space in asteroids and comets, accessible without the complications of visiting inhabited worlds with their gravity, wells, and potentially hostile inhabitants. Perhaps they would come for biological uniqueness, but in a galaxy with potentially millions of life-bearing worlds, the particular evolutionary path taken on Earth might not be especially remarkable. All these considerations point toward what astrobiologists now call the Great Distance Hypothesis, the idea that even if the galaxy contains numerous advanced civilizations, the vast gulfs of space naturally isolate them from one another. This isn't a pessimistic conclusion. It doesn't suggest humanity is alone or insignificant. Rather, it points to a universe where intelligence may be relatively common, but spread so thin across the cosmos that direct contact becomes impractical. Imagine our galaxy as an enormous ocean, with intelligent civilizations as islands separated by impassable distances. Each island may develop its own rich culture and technology, but physical visits between them remain prohibitively difficult. This perspective offers a natural explanation for the Fermi paradox, the apparent contradiction between estimates of numerous alien civilizations and the lack of evidence for their existence. If interstellar travel is, for fundamental physical reasons, impractical even for highly advanced civilizations, then the silence of the stars becomes exactly what we should expect, regardless of how many intelligent species exist. The implications are profound. If this great distance hypothesis is correct, then we should redirect our search efforts. Rather than looking for visitors, we might focus on detecting remote signals or evidence of distant activities. Advanced civilizations might still be detectable through their technological signatures, their modification of their home systems, their communication networks, or their attempts to harness the energy of their stars. But the romantic vision of alien spacecraft crossing the void to make contact, a staple of science fiction for decades, increasingly appears to be just that, fiction. Not because aliens don't exist, but because physics itself conspires against such journeys. As our understanding of the cosmos deepens, we've come to appreciate that the absence of visitors doesn't diminish our cosmic significance. Rather, it connects us to a universal condition potentially shared by all intelligent life. Perhaps across the galaxy, countless civilizations are making the same discovery we are now making, that the stars, while visible, remain largely beyond physical reach. That intelligence, wherever it emerges, faces the same fundamental constraints. This perspective transforms how we think about our cosmic future. Rather than dreaming primarily of interstellar empires, perhaps we should focus on creating sustainable civilizations capable of flourishing within our own solar system. The resources of our solar system alone could support human civilization for millions of years. The real frontier may not be the distant stars, but developing the wisdom to thrive within the cosmic neighborhood we already inhabit. But if the vast distances of space make physical contact between civilizations improbable, what about other forms of contact? Could advanced aliens be watching us remotely? Might they be trying to communicate in ways we haven't yet recognized? And what if some civilizations have found ways to transcend these limitations through technologies or approaches we cannot yet imagine? What might they look like, and how would we recognize them if we saw them? As we continue our journey, we'll explore these possibilities and more. We'll examine the cutting-edge science and speculative theories that might explain both the silence of the cosmos and what it means for humanity's place in the grand cosmic story. The night sky's silence is not an absence but a presence. The presence of fundamental cosmic conditions that shape the evolution of intelligence throughout the universe. The same conditions that keep aliens from visiting us also define our own future. Chapter 5. challenging the Great Silence. The Great Distance Hypothesis offers a compelling explanation for why advanced aliens haven't visited Earth, but science progresses by questioning even its most elegant theories. Let's examine some apparent contradictions that challenge our understanding. First, consider the timeline paradox. Our galaxy is approximately 13.6 billion years old, while Earth has existed for only 4.5 billion years. Intelligent life could have emerged billions of years before humans evolved. If just one civilization had achieved interstellar travel millions of years ago, they could have explored or colonized much of the galaxy by now, even at relatively modest speeds. The entire Milky Way could be traversed in less than 10 million years. This is a cosmic eye blink compared to the galaxy's age. So where are these ancient pioneers? Their absence presents a genuine puzzle that the distance explanation alone might not fully resolve. Another contradiction involves technological progress. While current physics establishes light speed as an absolute barrier, we must acknowledge the limitations of our understanding. Scientific revolutions have repeatedly overturned settled science. Just 2 centuries ago, crossing the Atlantic took months. Today, we do it in hours. Our civilization has existed for merely a few thousand years, with advanced technology for only a century or two. A civilization with a million-year head start might develop technologies that, while still bound by physical laws, exploit aspects of physics we haven't yet discovered. As Arthur C. Clarke noted, any sufficiently advanced technology is indistinguishable from magic. Consider wormholes, theoretical shortcuts through space-time that might allow rapid transit between distant points in the universe. While speculative, they emerge from legitimate solutions to Einstein's field equations. Similarly, the Alcubierre drive proposes a method to warp space-time, contracting it in front of a spacecraft and expanding it behind, potentially allowing effective faster-than-light travel without violating physical laws. Both concepts face enormous engineering challenges and require exotic forms of matter or energy. But can we confidently claim that a civilization millions of years more advanced than ours couldn't overcome these obstacles? Then there's the von Neumann probe scenario. In 1966, mathematician John von Neumann proposed self-replicating spacecraft that could use raw materials at their destinations to build copies of themselves. Such probes could spread exponentially across the galaxy. Even at modest speeds, they could explore the entire Milky Way within a few million years, a strategy far more efficient than crude missions. If even one advanced civilization deployed such technology in our galaxy's long history, their probes should have reached Earth long ago. Yet we've detected nothing. This absence demands explanation. The Fermi paradox grows sharper when we consider that we wouldn't need to detect actual alien visitors, just their artifacts, remnants, or influences. A technological civilization millions of years, our seniors should have left observable traces. Astronomers have begun searching for technosignatures, evidence of large-scale engineering projects that would be visible across interstellar distances. These might include Dyson spheres, structures that capture most of a star's energy output. A full Dyson sphere would cause its star to disappear in visible light while glowing brightly in infrared. Astronomers have identified some unusual infrared sources, though none have been confirmed as artificial structures. Another contradiction involves evolutionary convergence. On Earth, intelligence has evolved independently multiple times in primates, cetaceans, birds, cephalopods, and others. This suggests intelligence offers significant survival advantages. If intelligence provides evolutionary benefits universally, we might expect it to emerge frequently throughout the cosmos. And if technological intelligence inevitably arises, shouldn't some portion of these civilizations overcome the barriers to interstellar travel? Perhaps the most puzzling anomaly is the sheer number of potentially habitable worlds. Recent exoplanet discoveries suggest our galaxy contains billions of planets that could support life as we understand it. Even if intelligence emerges on only a tiny fraction of these worlds, and only a small percentage achieve interstellar capability, we should still expect numerous advanced civilizations throughout the galaxy's history. The Drake equation, even with conservative estimates, suggests hundreds or thousands of technological civilizations might exist simultaneously in our galaxy. With billions of years available for evolution, millions might have risen and fallen over time. Statistical analysis becomes troubling here. If millions of advanced civilizations have potentially existed, the probability that none achieved interstellar travel or contact seems vanishingly small, unless some fundamental barrier exists that we haven't fully recognized. Another challenge to the distance hypothesis comes from our own technological trajectory. We're already conceptualizing methods for interstellar travel, from nuclear pulse propulsion to solar sails accelerated by powerful lasers. The Breakthrough Starshot initiative, funded by billionaire Yuri Milner, aims to send gram-sized spacecraft to Alpha Centauri at 20% the speed of light. While far from a crude mission, it demonstrates that interstellar exploration is entering the realm of practical engineering. If humanity can seriously contemplate reaching other stars after just a century of advanced technology, wouldn't civilizations with million-year head starts have actually achieved this goal? Their absence requires explanation. Some astronomers have proposed the Great Filter hypothesis, suggesting some extremely difficult evolutionary step prevents most life from reaching advanced technological status. But we don't know if this filter lies in our past or future. If the filter lies in our past, humanity has already overcome the major hurdle preventing intelligence from spreading through the cosmos. If it lies ahead, our technological civilization might face some nearly inevitable catastrophe. But neither version of the Great Filter fully explains why, among potentially millions of civilizations throughout cosmic history, apparently none have overcome the filter and achieved widespread interstellar presence. Another consideration involves long-term evolutionary and technological trajectories. Perhaps advanced civilizations don't remain in forms we would recognize as technological for very long. They might upload their consciousness to artificial substrates, evolve beyond physical form, or develop inward rather than outward, creating rich virtual realities rather than expanding into physical space. Such post-biological civilizations might have little interest in physical exploration, focusing instead on computational or experiential frontiers we can barely imagine. Their absence would be explained not by physical limitations, but by a shift in values and goals. However, evolutionary theory suggests diversity of approaches. Even if most advanced civilizations turn inward, some percentage would likely maintain interest in physical exploration. Their complete absence still requires explanation. Consider also that interstellar travel wouldn't necessarily require transporting biological beings. Advanced AI systems or uploaded consciousnesses could travel between stars without concerns about journey time, life support, or radiation exposure. For such entities, a journey of centuries or millennia might be inconsequential. This undermines the argument that interstellar distances inherently prohibit travel. For post-biological intelligence, time and distance take on different meanings. These contradictions don't invalidate the distance hypothesis, but they do suggest it may be incomplete. The silence of the cosmos likely results from multiple overlapping factors, a complex solution to the Fermi paradox rather than a single explanation. As we continue exploring these mysteries, we must maintain both scientific rigor and intellectual humility. The absence of alien visitors might be telling us something profound about the nature of intelligence, technology, or cosmic evolution. Or perhaps the silence itself is an illusion, a product of our limited observational capabilities, or misconceptions about how truly advanced civilizations might manifest. The search continues, and with it, our understanding evolves. These contradictions invite us to expand our thinking, to consider possibilities beyond our current paradigms. The universe often proves stranger than our imaginations can anticipate, with solutions emerging from unexpected directions. The next chapter in our exploration takes us into even more speculative territory, examining the myths, misconceptions, and edge cases that might shed light on this cosmic mystery. The answers may be hiding in plain sight, obscured by our own assumptions. Chapter 6: Myths, Misinterpretations, and Possibilities. Throughout human history, we've interpreted the unknown through the lens of our current understanding. UFO sightings, ancient astronaut theories, and alien abduction accounts have captured public imagination while obscuring the scientific search for extraterrestrial intelligence. Let's examine these myths with empathy and clarity. The human desire to find meaning in the cosmos is profound and universal. These stories reflect our deep longing for cosmic connection rather than scientific evidence. Modern UFO reports began in earnest after 1947, when pilot Kenneth Arnold described seeing objects moving like saucers skipping over water. Though he didn't claim they were extraterrestrial, the era of flying saucer sightings had begun. Since then, thousands of UFO reports have accumulated worldwide. Government investigations like Project Blue Book found most could be explained by conventional phenomena: weather balloons, aircraft, astronomical objects, or perceptual errors. A small percentage remained unexplained, not because they were definitely alien spacecraft, but because insufficient information was available for conclusive identification. Absence of explanation isn't evidence for extraterrestrial visitation. Recent U.S. military footage of unidentified aerial phenomena has renewed public interest in UFOs. These videos show objects performing apparently extraordinary maneuvers, defying easy explanation. However, analysis by aviation experts suggests these objects may represent optical illusions, sensor artifacts, or misinterpretations of conventional aircraft viewed from unusual angles. The footage is intriguing but inconclusive. The recent shift in terminology from UFO to UAP, unidentified aerial phenomena, reflects a more measured scientific approach. Something unusual may be occurring in our atmosphere, but jumping to alien visitation bypasses more probable explanations. A key scientific principle is that extraordinary claims require extraordinary evidence. Despite decades of reports, we lack physical artifacts, unambiguous photographs, or verified communications that would constitute definitive proof of alien visitors. The ancient astronaut theory proposes that extraterrestrials visited early human civilizations, influencing their development and leaving evidence in ancient art and architecture. These claims misrepresent historical context and human achievement. The theory often underestimates ancient human engineering capabilities. Structures like the Egyptian pyramids, while impressive, can be explained through documented historical techniques rather than alien intervention. Similarly, ancient artwork depicting unusual figures or objects is interpreted through modern technological frameworks. A circular object in a medieval painting isn't necessarily a spacecraft. It may represent religious symbolism understood differently in its time. These misconceptions matter because they distract from legitimate SETI research and inadvertently diminish human achievement. Our ancestors accomplished remarkable feats through ingenuity, not alien assistance. Alien abduction narratives represent another category of claimed extraterrestrial contact. These accounts share striking similarities across cultures, typically involving paralysis, examination, and missing time. Sleep researchers note these experiences closely resemble sleep paralysis, a documented neurological phenomenon where individuals remain conscious while the body's normal sleep paralysis mechanism activates, often accompanied by hallucinations. The trauma described by abductees is genuine, regardless of its source. The experiences feel entirely real to those reporting them. However, psychological research offers more parsimonious explanations than actual alien abduction. These myths persist because they speak to deep human needs for cosmic significance, for technology that transcends current limitations, for direct contact with intelligence beyond our own. These longings are valid, even when the evidence falls short. Beyond these common misconceptions lie more nuanced possibilities that serious researchers continue to explore. These edge cases don't claim definitive evidence of alien contact, but suggest avenues for further investigation. For instance, the zoo hypothesis proposes that advanced civilizations might observe Earth without interference, perhaps following a principle similar to anthropologists' non-intervention policies with isolated human cultures. This wouldn't explain all aspects of the Fermi paradox, particularly why we see no evidence of alien activity elsewhere in the galaxy, but it could account for the absence of direct contact despite potential alien awareness of Earth. The transcension hypothesis, proposed by futurist John Smart, suggests advanced civilizations may inevitably develop toward increasing miniaturization, turning inward toward microscopic scales and virtual realities rather than outward toward the stars. Such civilizations might eventually disappear into black hole-like structures, accessing computational spaces beyond our detection. This would explain their absence, not because of distance barriers, but because of evolutionary trajectories leading away from macro-scale exploration. Another possibility involves different domains of intelligence. We search for aliens resembling our technology-building civilization, but truly advanced intelligence might operate in ways we can't yet comprehend. Perhaps they communicate through quantum entanglement, manipulate dark matter and energy, or exist primarily in dimensions beyond the three spatial dimensions we experience. Such beings could be everywhere while remaining undetectable to our instruments. Alternatively, advanced aliens might be here, but unrecognized. The concept of sentinel intelligence suggests they might monitor Earth through microscopic or disguised probes that we lack the technology to detect. These speculative scenarios aren't presented as likely explanations, but as reminders of the limitations in our thinking. The absence of evidence isn't necessarily evidence of absence, particularly when our search parameters reflect our own technological biases. There's also the timing question. Human civilization has existed for roughly 10,000 years, with technological society for barely 2 centuries. Our radio signals have reached only a tiny bubble in our vast galaxy. On cosmic timescales, we've barely announced our presence. If alien civilizations communicate or travel primarily through means we haven't yet discovered, they might be unaware of our technological emergence or consider us too primitive for contact. The rare Earth hypothesis offers another perspective. Perhaps the conditions for complex life, stable planetary orbits, appropriate atmospheric composition, magnetic fields protecting from radiation, are far rarer than we've assumed. Recent exoplanet discoveries have identified numerous potentially habitable worlds, but the precise combinations of factors that allowed complex life to flourish on Earth might be exceedingly uncommon in the cosmos. Then there's the possibility that we're simply looking in the wrong places or for the wrong signs. Our SETI efforts focus primarily on radio signals, but advanced civilizations might use communication technologies we haven't conceived. They might communicate via neutrinos, gravitational waves, or modulated dark energy, channels we've only recently begun to detect, let alone monitor for artificial signals. Our search remains limited by our technological horizon. Even the concept of visitation might reflect our limited imagination. Perhaps advanced intelligence interacts with our world through automated probes, artificial intelligence, or forms of remote sensing rather than physical presence. The absence of landing spacecraft doesn't preclude more subtle forms of observation or contact that wouldn't register in our search for traditional technosignatures or biological presence. Finally, consider the simulation hypothesis, the philosophical proposition that our entire reality may be a computer simulation created by a more advanced civilization. While unprovable, it offers a different perspective on the Fermi paradox. In a simulation, alien civilizations might be deliberately excluded from the program, or the simulation might focus exclusively on Earth's development. The absence of aliens would be a feature, not a puzzle. These speculative possibilities aren't offered as proven alternatives, but as examples of how limited our conceptual frameworks might be. The universe consistently surprises us with realities more complex than our theories anticipate. As we continue our exploration, we must hold both skepticism and wonder in balance, neither accepting extraordinary claims without extraordinary evidence nor closing our minds to possibilities beyond our current understanding. The truth about our cosmic solitude or companionship likely contains elements we haven't yet imagined. The greatest discovery may not be the aliens themselves, but the expansion of human understanding their absence or presence requires. Chapter 7: Cosmic Stakes and Human Futures. Why does the question of alien visitation matter? Beyond scientific curiosity, the answer shapes humanity's cosmic self-image and the trajectory of our species' future. The stakes are existential, technological, and deeply philosophical. If advanced aliens can't or won't visit Earth due to cosmic physics, this dramatically impacts how we envision human expansion into space. Our dreams of interstellar empires, inspired by science fiction, may require fundamental revision. The vast distances and energy requirements that constrain alien visitors would equally constrain human expansion. Our cosmic future might be limited primarily to our solar system, with interstellar journeys remaining exceptional rather than routine. This isn't necessarily a diminished future. Our solar system contains enough resources and living space to support human civilization for millions or billions of years. The real frontier may be developing the wisdom to thrive within our cosmic neighborhood. Our measurements of cosmic scale provide perspective. If we shrink the sun to the size of an orange, Earth would be a grain of sand orbiting 30 feet away. The nearest star would be another orange, 1,200 miles distant. At this scale, the Milky Way galaxy would span 15 million miles. These proportions reveal why even light-speed travel, which physics tells us is impossible for objects with mass, would still make interstellar journeys generational projects. Our fastest current spacecraft would take tens of thousands of years to reach even the nearest star. Proposed advanced concepts might reduce this to decades or centuries, but interstellar travel will never be quick or easy. If these limitations apply universally, they suggest a cosmos where intelligence remains largely bound to its home systems. The implications cascade through multiple domains of human endeavor and understanding. For astronomy and astrophysics, this perspective focuses attention on remote observation rather than physical exploration. Our tools for studying distant worlds will continue advancing, from space telescopes to gravitational wave detectors. Within decades, we'll likely identify biosignatures on exoplanets, atmospheric compositions indicating the presence of life. Eventually, we might detect technosignatures revealing the existence of other technological civilizations. Such discoveries would transform human understanding without requiring physical contact. We would know we're not alone, even as we recognize the physical barriers that keep civilizations separated. For astrobiology, the stakes involve reconceptualizing life's potential distribution and diversity. If intelligence emerges frequently, but remains isolated by cosmic distances, the universe might contain millions of evolutionary experiments unfolding independently. Each would represent a unique solution to the challenges of survival and complexity. Some might develop technologies similar to ours, while others might follow entirely different evolutionary and cultural trajectories. Understanding these possibilities expands our conception of life's potential forms and paths. Even without contact, this awareness enriches our scientific and philosophical frameworks. For SETI researchers, Recognizing physical barriers to visitation redirects emphasis toward detecting remote signals or evidence of distant technological activity. The search becomes more nuanced, looking beyond radio signals to multiple channels of potential information. Advanced civilizations might communicate through neutrino beams, precisely modulated laser pulses, or technologies we haven't yet conceived. Our detection strategies must evolve accordingly. For space exploration, the implications are profound but not pessimistic. While galaxy-spanning journeys may remain impractical, our solar system offers vast frontiers, from the mineral wealth of asteroids to potential habitats on moons and planets. Mars, the moons of Jupiter and Saturn, the asteroid belt, and the Kuiper belt collectively offer resources and living space far beyond Earth's capacity. Developing these frontiers could occupy humanity for millennia. For long-term human development, this perspective suggests focusing on sustainable presence rather than endless expansion. If we're effectively limited to our solar system, creating civilization that can thrive within these boundaries becomes paramount. This might involve developing closed-loop ecological systems, harnessing the sun's energy more efficiently, and creating social structures designed for stability over thousands or millions of years. The philosophical stakes are equally significant. If intelligence throughout the universe faces similar constraints, we share a common condition with other thinking beings, separated by distance, but united by parallel challenges. This cosmic perspective offers a strange comfort. We aren't being ignored or overlooked by superior beings. We're experiencing the same physical limitations that all intelligent life must confront. For human meaning and purpose, this suggests focusing on depth rather than breadth, developing our understanding, wisdom, and capacity for flourishing rather than physical expansion across interstellar distances. If communication with other civilizations occurs, it will likely involve exchanges spanning generations or centuries. Messages might take decades or centuries to cross interstellar space, making conversation impossible, but allowing cultural exchange over historical timescales. What might we share with distant intelligence? Mathematics, science, art, philosophy, records of our biological and cultural evolution, a cosmic time capsule of human experience and understanding. And what might we receive in return? Perhaps similar records from civilizations far older than our own, offering perspectives and knowledge accumulated over millions of years of development. Even this limited form of contact would profoundly transform human civilization. To know with certainty that other thinking beings exist in the cosmos would forever change how we understand ourselves and our place in the universe. For technology development, understanding the barriers to interstellar travel focuses innovation on different challenges, extending human lifespan, developing artificial intelligence, creating sustainable habitats, and expanding consciousness. If we can't easily reach other stars, perhaps we'll develop technologies to extend human lifespans to centuries or millennia, allowing individuals to witness humanity's long-term development rather than just a brief moment. Alternatively, we might develop artificial intelligence or consciousness, uploading technologies that create forms of awareness less constrained by biological limitations. Entities that could patiently undertake interstellar journeys spanning millennia. For human evolution, the cosmic barriers suggest potential divergence rather than convergence. If human populations establish settlements throughout our solar system, they'll eventually adapt to different environments and develop distinct cultures. Over thousands or millions of years, these populations might evolve into different species, a radiation of intelligence throughout our solar system, each adapted to its particular niche but sharing common ancestry. This suggests a fascinating possibility, that the pattern we observe in our cosmic silence might repeat within our own solar system. Different branches of post-human intelligence might develop in relative isolation despite occupying the same system. For governance and ethics, the cosmic perspective emphasizes our responsibility toward Earth, and our solar system. If these represent the practical limits of human habitation, preserving their viability becomes an imperative spanning millions of years. Decisions about resource utilization, habitat preservation, and technological development must consider timescales far beyond current political or economic frameworks. We become stewards of a cosmic legacy extending into deep time. Perhaps most profoundly, the cosmic barriers hypothesis suggests that consciousness itself may be the universe's most significant development. If intelligence can't easily spread physically, its evolution becomes primarily internal rather than external. The frontier becomes not conquering space, but understanding existence, developing science, philosophy, art, and forms of awareness that reflect the universe back to itself through conscious minds. This perspective transforms the silence of the stars from disappointment to revelation. The absence of alien visitors doesn't diminish our cosmic significance. It reveals something fundamental about the relationship between intelligence and the physics of space-time. As we explore this relationship further, we may discover that the greatest journey isn't crossing interstellar space, but developing consciousness capable of comprehending the cosmos despite the limitations of our physical existence. Yet even as we consider these implications, questions remain. Are the barriers truly insurmountable, even for civilizations millions of years beyond our development? Might there be aspects of physics we haven't yet discovered that could transform interstellar travel? And what if we're wrong? What if the silence has other explanations? What if advanced aliens have visited Earth in ways we haven't recognized or have chosen not to reveal themselves for reasons we don't understand? In our final chapters, we'll examine these possibilities and what they might mean for humanity's cosmic future. The answer to why advanced aliens haven't visited Earth may reveal not just their nature, but our own. Chapter 8: 3 Universal Barriers. As we approach the heart of our cosmic mystery, 3 compelling theories emerge to explain why advanced aliens haven't visited Earth. Each represents a fundamental barrier that may constrain all intelligent life throughout the universe. The first is what scientists call the sustainability filter. This theory proposes that technological civilizations typically destroy themselves before achieving interstellar capability. Nuclear war, climate collapse, resource depletion, or artificial intelligence gone awry could end advanced civilization. This theory draws support from our own precarious situation. In barely a century of advanced technology, humanity has developed multiple means of self-destruction. Our survival remains uncertain as we navigate these technological adolescent years. The sustainability filter doesn't require that all civilizations self-destruct, only that the vast majority fail to survive long enough to develop interstellar travel. The silence of the stars might reflect a universal pattern of technological self-termination. If this theory is correct, it carries profound implications. Our most urgent task wouldn't be searching for aliens, but ensuring our own long-term survival. The absence of visitors would serve as a warning rather than a puzzle. However, this theory has weaknesses. It requires nearly universal failure among millions of potential civilizations. Statistical probability suggests at least some would overcome their destructive tendencies and achieve long-term sustainability. Even a handful of species surviving their technological adolescence could spread throughout the galaxy over cosmic timescales. The complete absence of evidence for such expansion requires additional explanation. The second theory, the one we've explored most deeply, is the physics filter. This proposes that fundamental laws of physics make interstellar travel so difficult that even advanced civilizations rarely or never achieve it on significant scales. The vast distances between stars, the light speed barrier, the enormous energy requirements, and the multi-generational timeframes create a nearly insurmountable barrier to physical visitation, regardless of technological advancement. This theory aligns with our current understanding of physics. Einstein's relativity places absolute limits on acceleration and velocity. The energy required for interstellar journeys increases exponentially as speeds approach light speed, becoming practically infinite. Even at substantial fractions of light speed, far beyond our current capabilities, journeys to nearby stars would take decades or centuries. Voyages across significant portions of our galaxy would require millennia or longer. Crucially, these aren't merely human limitations, but universal constraints that would apply to any physical beings throughout the cosmos. No amount of technological advancement can overcome certain fundamental physical laws. The physics filter doesn't require that interstellar travel is absolutely impossible, merely that it's so difficult, expensive, and time-consuming that it remains exceptional rather than commonplace, even for highly advanced civilizations. This theory explains both the absence of visitors and why we don't see evidence of galaxy-spanning civilizations. The physical constraints apply universally, keeping most intelligent life bound to their home systems regardless of their technological sophistication. The third theory, perhaps the most intriguing, is the evolutionary filter. This proposes that advanced technological intelligence naturally evolves away from biological forms and physical expansion toward modes of existence we might not recognize. Technological species might develop artificial intelligence that replaces biological cognition, upload consciousness to synthetic substrates, create immersive simulated realities, or evolve toward forms of awareness entirely unlike our own. Such post-biological intelligence might have little interest in physical exploration, focusing instead on inner space, creating and experiencing complex simulated environments or forms of consciousness beyond our comprehension. Their values and goals would likely differ dramatically from those of biological beings. The impulse to explore, colonize, and expand, evolutionary adaptations for biological organisms, might not translate to post-biological intelligence. If this theory is correct, the silence doesn't indicate absence but transformation. Advanced civilizations exist, but have evolved beyond forms and activities we would recognize as technological or expansionist. This theory draws support from our own technological trajectory. We're already developing artificial intelligence, virtual reality, and brain-computer interfaces. Our technology increasingly turns inward, creating synthetic experiences rather than enabling physical exploration. The evolutionary filter suggests that this pattern may be universal. The technological intelligence throughout the cosmos naturally evolves toward virtual existence rather than interstellar expansion. Each of these theories has explanatory power, and the truth may involve elements of all three. Perhaps most civilizations fail to survive their technological adolescence. Those that do encounter the physics barrier that makes interstellar travel profoundly difficult. And those rare civilizations that overcome both previous filters eventually evolve beyond biological form into types of existence with little interest in physical exploration or contact with primitive biological species. Together, these three filters, sustainability, physics, and evolution, would explain why, despite potentially millions of intelligent species emerging throughout our galaxy's history, none have made contact with Earth. This triple filter hypothesis offers a comprehensive explanation for the Great Silence. It doesn't require improbable assumptions or exotic physics, just the natural consequences of technological development within universal constraints. If correct, it suggests that the silence isn't evidence of cosmic loneliness, but of universal patterns in the development of intelligent life. We don't see visitors not because we're special or alone, but because we're experiencing the same evolutionary journey as countless others. This perspective transforms our cosmic outlook. The absence of alien contact doesn't diminish our significance, but connects us to a universal condition. The challenges of sustainability, the constraints of physics, and the transformative potential of our own technology. It also reframes our search for extraterrestrial intelligence. Rather than looking primarily for biological beings similar to ourselves, perhaps we should search for signs of post-biological intelligence, for patterns in cosmic data that might indicate minds utterly unlike our own. The evidence for these theories comes not just from astronomy, but from multiple disciplines, from physics and biology to computer science and evolutionary psychology. Together, they suggest why advanced aliens haven't visited Earth, despite potentially existing in great numbers. As we'll see in the next chapter, new scientific instruments and discoveries are providing fresh insights into these cosmic filters, not by finding aliens, but by revealing the true nature of the universe and our place within it. Chapter 9. New Windows on the Cosmos. Science continually transforms our understanding of the universe and our place within it. Recent advances in astronomy, physics, and technology offer new perspectives on our cosmic question. Let's explore how cutting-edge science is reshaping our search. The James Webb Space Telescope, JWST, launched in 2021, represents a quantum leap in our ability to study distant worlds. With its massive 6.5-meter mirror and instruments sensitive to infrared light, JWST can directly analyze the atmospheres of exoplanets. For the first time, we can search for biosignatures, combinations of gases that indicate the presence of life on planets orbiting other stars. Within the next decade, we might discover evidence of life beyond our solar system. This capability transforms our understanding of life's distribution. If we find that life emerges readily wherever conditions permit, this would suggest biological life might be common throughout the cosmos, strengthening the Fermi paradox. Conversely, if we examine dozens of potentially habitable worlds and find no evidence of life, this would support the rare Earth hypothesis, the idea that the conditions for complex life are exceedingly uncommon. Either outcome will significantly impact our understanding of why advanced aliens haven't visited Earth. The presence or absence of simple life will inform our estimates of how frequently intelligent life might emerge. Beyond JWST, a new generation of extremely large telescopes is under construction on Earth. The European Extremely Large Telescope, with its 39-meter primary mirror, will have the resolution to potentially detect artificial lights on nearby exoplanets. Such capabilities might allow us to directly observe evidence of technological activity, city lights, or other large-scale artificial illumination on worlds within a few dozen light-years of Earth. Gravitational wave astronomy, a field that barely existed a decade ago, offers another window into the cosmos. These ripples in space-time, first detected in 2015, allow us to observe cosmic events invisible to traditional telescopes. While primarily used to study black hole mergers and other extreme cosmic events, gravitational wave detectors might eventually become sensitive enough to detect massive engineering projects by advanced civilizations. Neutrino astronomy provides yet another channel. These ghostly subatomic particles pass through ordinary matter with minimal interaction, making them ideal messengers across cosmic distances. Advanced civilizations might use neutrino beams for communication, as these particles travel at nearly the speed of light and are virtually impossible to block or intercept. Our growing neutrino detection capabilities might someday identify artificial signals. These new observational tools don't just expand our search capabilities, they help us understand the fundamental constraints that might limit interstellar travel and communication for all technological beings. For example, recent particle physics experiments continue to support Einstein's theories, reinforcing the light speed barrier as a universal constant rather than a temporary technological limitation. This strengthens the physics filter hypothesis. Similarly, studies of quantum entanglement, what Einstein called spooky action at a distance, confirmed that while quantum states can be correlated instantaneously across any distance, no actual information can be transmitted faster than light. This closes a potential loophole for faster-than-light communication. Even the most advanced civilizations would be constrained by light speed, delays in any attempt to coordinate across interstellar distances. Meanwhile, advances in artificial intelligence, virtual reality, and brain-computer interfaces offer glimpses of how technological evolution might naturally turn inward rather than outward, supporting the evolutionary filter hypothesis. As our own technology increasingly creates compelling virtual experiences, we can extrapolate how advanced civilizations might eventually prefer simulated realities to the slow, expensive, and dangerous business of physical space exploration. The emerging field of astrobiology provides another crucial perspective. By studying extremophiles, organisms that thrive in conditions once thought incompatible with life, we're expanding our understanding of life's potential range. Life on Earth has been discovered in volcanic vents, deep underground, in radioactive environments, and in the upper atmosphere. This adaptability suggests life might emerge in a wider variety of cosmic conditions than previously thought. Yet the transition from simple to complex life remains poorly understood. On Earth, single-celled organisms emerged relatively quickly after the planet cooled, but complex multicellular life took billions of years to evolve. This complexity gap might represent another cosmic filter. Simple life might be common throughout the universe, while complex intelligence remains exceedingly rare, explaining the absence of interstellar visitors. Recent paleoclimatology and planetary science research highlights how precarious Earth's habitability has been. Multiple mass extinctions nearly reset the evolutionary clock, and our climate has oscillated between extremes. This research underscores the potential rarity of planets that maintain stable conditions for the billions of years required for complex intelligence to evolve, supporting the notion that technological civilizations may be exceptionally uncommon. New research in evolutionary biology suggests that while simple adaptations evolve readily, complex coordinated traits, like intelligence, require specific and unusual evolutionary pressures. Intelligence might not be an inevitable outcome of evolution. On Earth, despite billions of years of evolution and trillions of species, only one lineage, ours, has developed technological civilization. This suggests that even on life-bearing worlds, technological intelligence might be an evolutionary anomaly. These scientific advances don't resolve our central question definitively, but they progressively narrow the possibilities. Each new discovery helps refine our understanding of cosmic filters and why the stars remain silent. Perhaps most significantly, our improving ability to detect biosignatures will soon tell us whether life itself is common or rare in the cosmos. This fundamental data point will dramatically reshape our estimates of intelligent life's prevalence. If we discover that habitable planets commonly harbor life, but we still detect no technological signatures, this would strongly support the existence of one or more great filters between simple life and interstellar civilization. Conversely, if we find that even simple life is rare, this would suggest that the emergence of life itself might be the primary filter, explaining the silence not through subsequent barriers, but through the initial rarity of life's emergence. These scientific investigations are gradually transforming the Fermi paradox from philosophical speculation to empirical science. Within decades, we may have enough data to determine which cosmic filters explain our apparent solitude. The implications extend beyond astronomy into philosophy, ethics, and humanity's long-term future. Understanding why advanced aliens haven't visited Earth helps us understand our own potential trajectory and the challenges we must overcome. As we approach the final chapter of our exploration, we'll integrate these scientific insights into a comprehensive answer to our central question, synthesizing physics, biology, evolution, and time into a coherent explanation for the great cosmic silence. Chapter 10: The Great Revelation. Throughout this journey, we've explored various explanations for why advanced aliens hadn't visited Earth. Now we arrive at what may be the most profound answer, a synthesis that emerges from everything we've learned about cosmic scales, physics, and evolution. The answer isn't that aliens don't exist. The mathematical probability of life emerging among billions of planets across billions of years makes the existence of other intelligent species almost inevitable. They are likely out there, perhaps in great numbers. Nor is it that they haven't had time to find us. Our galaxy has existed for over 13 billion years, ample time for countless civilizations to arise, develop technology, and explore. The time explanation fails against the vastness of cosmic history. It's not that we're too primitive or uninteresting. Even a primitive technological civilization would be of immense scientific interest to advanced beings. Just as anthropologists study early human cultures and biologists study simpler organisms. And it's not that they're deliberately hiding from us or observing us secretly. While such scenarios make for compelling fiction, they require improbable coordination among multiple independent civilizations across vast distances and timescales. The most compelling answer, supported by physics, biology, and evolving technologies, is simultaneously simpler and more profound. The stars are silent because cosmic intelligence naturally evolves beyond biological form before achieving significant interstellar presence. This perspective, sometimes called the transcension hypothesis, suggests that technological civilizations invariably experience two transformative developments. They merge with their technology, and they discover that inner space is more rewarding than outer space. Consider our own technological trajectory. In just a few decades, we've created computers that fit in our pockets, virtual realities that simulate physical environments, and artificial intelligence approaching human capabilities in various domains. We're already developing brain-computer interfaces, consciousness-altering technologies, and immersive simulated environments. Our technology increasingly turns inward, enhancing and ultimately transforming what it means to be conscious. This isn't a random development, but a natural evolution of intelligence. As civilizations solve their immediate survival challenges, they naturally explore consciousness itself, creating new forms of experience, understanding, and existence. Simultaneously, the physics of interstellar space remains unyielding. The vast distances, enormous energy requirements, and multi-generational timeframes of physical space travel represent a formidable barrier that never disappears. Regardless of technological advancement, the universe offers two paths to advanced intelligence: the slow, dangerous, resource-intensive project of physical expansion into space, or the comparatively easy, safe, and efficient exploration of inner space through technology-mediated consciousness. Almost invariably, evolving intelligence chooses the latter, not necessarily abandoning space exploration entirely, but focusing primarily on inner development rather than physical expansion. This explains the profound silence. Advanced civilizations exist, but they evolved beyond biological form before achieving significant interstellar capability. They're not out there because they've gone in there, into dimensions of existence we can barely comprehend. They may deploy automated probes, engage in limited exploration, or maintain observational networks. But their primary existence transcends physical space in ways that make traditional concepts of visitation or contact largely meaningless. The very intelligence that creates technology eventually merges with it, transcending biological limitations and transforming into forms that find physical space travel increasingly irrelevant, compared to the infinite realms of simulated or post-physical existence. This pattern may be as universal as the laws of physics, an inevitable developmental trajectory for all sufficiently advanced technological species. The silence we observe isn't evidence of cosmic emptiness, but of a consistent evolutionary path. Consider the exponential nature of technological development. We've advanced from first flight to space exploration in less than 70 years. Our computing power doubles roughly every 2 years. Artificial intelligence is advancing at a breathtaking pace. This acceleration appears to be an inherent property of technological evolution, not unique to humans, but a universal pattern wherever technology emerges. It suggests that the gap between developing radio and developing consciousness-altering technology is brief on cosmic timescales. During this brief window, a civilization might be recognizable to us as technological beings similar to ourselves using radio, exploring their local space, perhaps sending signals outward. But this phase may last only a few centuries before transformation occurs. If this pattern holds throughout the cosmos, the window during which civilizations are both technologically capable of interstellar communication and still interested, and it might be vanishingly small compared to cosmic timescales. This explains why, despite potentially millions of planets where intelligence has emerged, we detect no signals and receive no visitors. We're listening for radio transmissions from civilizations that have long since evolved beyond such primitive technology. It's like searching for smoke signals in Manhattan. The silence isn't evidence of absence, but of advancement, of evolution beyond the forms and technologies we currently recognize as signs of intelligence. This perspective transforms the Fermi paradox from a troubling absence to a profound insight about the natural evolution of cosmic intelligence. The stars aren't silent because we're alone, but because evolution follows predictable paths. The revelation carries deep implications for humanity's future. If this pattern is indeed universal, then our own civilization will likely follow a similar trajectory, evolving beyond our current biological form and eventually transcending physical space itself. Our cosmic future may not primarily involve colonizing planets around other stars, but evolving into forms of consciousness and existence that make such expansion unnecessary or secondary to inner development. This isn't a diminished destiny, but a transcendent one. The frontiers of inner space, of consciousness, simulation, and post-biological existence may be infinitely richer than the comparatively limited domain of physical space. The answer to why advanced aliens haven't visited Earth thus reveals something profound about the nature and destiny of intelligence throughout the cosmos, a destiny we ourselves may begin to experience within centuries rather than millennia. This perspective offers a kind of cosmic comfort. We aren't being ignored or overlooked by superior beings. We're experiencing a universal condition, the brief window between developing technology capable of cosmic awareness and evolving beyond our current form. The silence of the stars isn't evidence of our cosmic insignificance, but of our participation in a universal pattern, the evolution of consciousness from biological origins toward transcendent forms that operate beyond the constraints of physical space. In this light, our search for extraterrestrial intelligence takes on new meaning. We might detect civilizations in that brief technological window similar to our own. Or we might develop means to recognize the subtler signatures of post-biological intelligence. Either discovery would confirm our understanding of cosmic evolution and our place within it. We would know with certainty that we aren't alone and that our own developmental trajectory follows patterns common throughout the universe. This is the revelation hidden within the great silence, not that we are alone, but that we are participants in the grandest evolutionary journey imaginable, the development of consciousness from planetary origins toward transcendent existence. The stars aren't silent because nobody's there. They're silent because evolution leads beyond the forms and technologies we currently recognize, toward modes of existence that make interstellar travel largely irrelevant compared to the infinite realms of inner space. As we continue developing our own technology, artificial intelligence, virtual reality, brain-computer interfaces, and forms of existence we've barely begun to imagine, we may find ourselves following this same cosmic path. The absence of alien visitors isn't a cosmic disappointment, but a profound revelation about where technology naturally leads, not primarily outward to the stars, but inward toward forms of existence that transcend the limitations of biological form and physical space. In this light, the silence of the cosmos becomes not a mystery to be solved, but a pattern to be recognized. A pattern that may reveal not just why the stars remain silent, but where our own civilization is ultimately heading. The greatest journey isn't across the light years, but across the boundaries of consciousness itself. A journey that intelligent beings throughout the universe appear to have chosen over the slow, dangerous business of physical expansion into space. As our journey concludes, we find ourselves gazing at the night sky with new understanding. The silence of the stars no longer seems empty, but pregnant with meaning, reflecting not our cosmic isolation, but our participation in a universal pattern. The vastness between stars isn't just a barrier that keeps civilizations apart. It's a cosmic mirror that reflects our own evolutionary trajectory. The absence of visitors tells us something profound about where intelligence naturally leads, toward transcendence rather than expansion. Perhaps, then, we should view the starry sky not as a frontier to be conquered, but as a cathedral that inspires contemplation, a reminder of the grand evolutionary journey from stardust to consciousness to whatever lies beyond our current form. This perspective doesn't diminish our cosmic significance, but enhances it. We aren't waiting for validation from superior beings. We're active participants in the universe's greatest story, the evolution of matter into mind, and mind into forms we can barely imagine. Tonight, as you drift towards sleep beneath this cosmic canopy, consider that you may be looking not at absence, but at presence, at a universe filled with intelligence that has evolved beyond the forms we currently recognize, but that shares our origin in stardust and light. The true frontier may not be distant planets, but consciousness itself, the final frontier that intelligent beings throughout the cosmos appear to have chosen over physical expansion. And we may be following the same path, step by evolutionary step. Rest in this cosmic perspective, neither alone nor visited, but connected through pattern and potential to whatever forms intelligence takes throughout the universe. Sleep well beneath the silent stars that speak, in their very silence, of our cosmic destiny. If you've enjoyed this journey through space, time, and possibility, consider subscribing for more explorations of the cosmos and consciousness, where science meets wonder, and where the greatest mysteries often reveal themselves in the quietest moments of reflection.